Welcome students. In this video we are going to see what are the specific heats, Cp and Cv values for different types of gases. Okay, right? Gases, we can divide them into one, monoatomic gases. Monoatomic gases means, what is a molecule? Molecule is something which has two or more atoms is known as a molecule. Okay, monoatomic gases means it is having only one atom. Examples are noble gases like helium, neon, argon, etc. There is only one atom, that's all. It is known as monoatomic gas. Monoatomic gas. Okay, second one, diatomic gases. Okay, diatomic gases. What are diatomic gases? Atoms, molecules which are what you call gases which have two atoms in the molecule, like H2, N2, O2, okay, or CO, carbon monoxide, or HCl, like this. Okay, these are known as diatomic gases. Here the molecule contains two atoms. Okay, if both atoms are of same type, we call it as homonuclear molecules. If both are different types of atoms like CO, HCl, HBr, etc., we call it as heteronuclear. Hetero means different. Heteronuclear atoms. Okay, homo means similar. Okay, homonuclear molecules H2, N2, O2, CO, HCl, they are heteronuclear molecules. Whatever it is, they are diatomic molecules. They have two atoms. Okay, next one, triatomic molecules. Triatomic molecules like H2O, okay, SO2, right, N2O, etc. These molecules have three atoms in the molecule. These gases have three atoms in each molecule. These are known as triatomic gases, diatomic gases, and monoatomic gases. Okay, now we have to see, right, what are Cv value and Cp values for each of these gases. Okay, in the last video we have seen, okay, Cp and Cv, we have defined Cp and Cv values. Okay, how did we get Cv? Molar specific at constant volume, Cv equal to dq by dt. Okay, at constant volume. Okay, at constant volume, I'll put write this volume as a subscript outside the brackets. It indicates that the process is a constant volume process. Okay, molar specific constant pressure Cp equal to the amount of heat required to raise the temperature of 1 mole of gas through 1 degree Celsius. Okay, at a constant pressure. dq by dt at constant P is Cp, dq by dt at constant V is Cv. Moreover, according to first law of thermodynamics, okay, delta or dq equal to, right, du plus pdv. In a constant volume process, what will happen? Volume remains constant means change in volume dv becomes 0. So work done by the gas is equal to 0. So wherever dq is there, you can simply write it as a du also. So especially for Cv, we can write dq by dt at constant volume or du by dt at constant volume. Du by dt. The moment I write constant du, it is understood that it is constant volume process, or du we can write it as Cv dt for 1 mole, okay, or right, for n moles du equal to n Cv dt. Okay, these are the things which we have already covered in our last video. Now we will see what are Cp and Cv values for monoatomic, diatomic and triatomic gases. Okay, now there is one law called Boltzmann's law of equidistribution of energy. Boltzmann's law of equidistribution of energy, that is, which says what? The average energy per molecule per degree of freedom is equal to half kT, half k into T. This is called Boltzmann's law of equipartition of energy. Okay, Boltzmann's law of equipartition of energy, average energy per molecule, average kinetic energy per molecule per degree of freedom is equal to half kT. K is a constant called Boltzmann's constant. K is a constant called Boltzmann's constant. Okay, its value is K equal to 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, T is absolute temperature. Okay, per molecule per degree of freedom, average energy is half kT. Okay, what is a degree of freedom? What is degree of freedom means? Number of degrees of freedom for a molecule is equal to number of independent ways in which it can acquire its total energy. Okay, means in how many ways it can acquire its total energy, right, will decide how many degrees of freedom it has. Now, suppose a particle can move only along x-axis, say its total energy, that is kinetic energy or potential energy, all are related to x-axis only. I will say it has only 1 degree of freedom. Okay. Whereas a particle can move along x-axis or can move along y-axis also. It can move in 2 different ways. In 2 different ways, it can have its kinetic energy and potential energy, say, right? Just like this pen. Okay, this I can move this pen anywhere on the board. Either I can move along x-axis like this, or only along y-axis like this, or along x-y axis like this on this plane. Means the number of degrees of freedom, right, my pen has, right? My pen can write only on the board, isn't it? It cannot write in air. It cannot leave the board and come. Okay, right? It makes sense only on the board. So the number of degrees of freedom which my pen has is equal to 2 degrees of freedom. Means 2-dimensional motion, 2 degrees of freedom it has. Whereas a bird is there. Okay, bird can move along x-axis or can move along y-axis, or it can move along z-axis also. Bird can fly like this. It can move, right, in 3 dimensions simultaneously. So a bird has 3 degrees of freedom. I throw my pen like this. Okay, this pen is having a 3-dimensional motion, so the number of degrees of freedom, right, will be equal to 3. So number of independent ways a system can acquire its total energy is known as number of degrees of freedom. Okay, right? Now, so what is this Boltzmann's law of equipartition of energy? Okay, average energy per molecule per degree of freedom is half kT. So we have to keep on seeing how many degrees of freedom a molecule has. It depends on its atomicity. It means how many atoms are there in that molecule. Okay, now we will see, evaluate one by one. Okay, first we take what is known as a monoatomic gas. First one is monoatomic gas. Examples already we have seen: helium, okay, neon or argon, like this. Okay, helium atom, 1 atom only is there. 1 atom in a vessel. Okay, this single atom of helium can move along x-axis or can move along y-axis, or it can move along z-axis also. Means the molecule in a gas can move along x-axis or y-axis or z-axis. Means the number of degrees of freedom, right, this molecule has or atom has 3 degrees of translational motion, because particle is moving from one point to another point. Okay, so number of degrees of freedom for this gas is equal to, okay, the number of degrees of freedom for this gas, right, monoatomic gas, each atom has 3 degrees of freedom. So number of degrees of freedom, okay, should not put a small, what you call, circle on the head. Okay, degrees mean degree only we are supposed to write. Okay, number of degrees of freedom is equal to 3, that is translational motion. Okay, the degrees, 3 degrees of translational motion. What is Boltzmann's law of equipartition of energy saying? Boltzmann's law of equipartition of energy saying that the average energy per molecule, per degree of freedom is equal to half kT. We are saying this our molecule, our atom has 3 degrees of freedom. Therefore, the average energy per atom is equal to how much? Average energy per atom is equal to, okay, average energy per atom is equal to 3 into half kT. That is equal to 3 by 2 kT. Okay, this is for 1 atom. 1 mole of any gas contains, right, Avogadro number of atoms. Avogadro number 6.023 into 10 to the power 23 atoms per gram mole is usually denoted by N. Avogadro number. So for each molecule, this is the average energy. So for N molecules, for the entire gram mole of gas, what is the total energy of 1 gram mole of gas? What is total energy? That is kinetic energy. Okay, total kinetic energy of all the molecules in 1 mole of gas is nothing but internal energy. Okay, so what is internal energy of the gas? Okay, every molecule has 3/2 kT energy. There are n number of molecules, so total energy of all the n number of molecules, that is nothing but the total kinetic energy of all molecules in 1 mole, nothing but internal energy we call. Okay, so it is nothing but 3/2 nkt. 3/2 nkt. N is Avogadro number, a constant. K is Boltzmann's constant. This is also constant. N into K will also be a constant. I'll write this as 3/2 RT. Okay, right, where R is nothing but our gas constant, molar gas constant, 8.31 joule per mole Kelvin. Joule per mole Kelvin. Okay, so gas constant is nothing but, right, Avogadro number multiplied by Boltzmann's constant. This is a constant for 1 mole of gas. For each molecule, what is the gas constant? When I'm talking about an individual atom or a molecule, we will use the constant as K. So Boltzmann's constant is a gas constant for each molecule, whereas R is gas constant for 1 mole. How to get the constant for 1 mole from an individual atom or molecule? Multiply it with Avogadro number. So N into K is equal to R, remember. Okay, N into K is equal to our gas constant R. So U equal to 3/2 RT. This is the internal energy. Okay, in the last video we have seen molar specific at constant volume Cv equal to du/dt we can write. Okay, so what happens to Cu now, right? Cv equal to d/dt of U. U equal to 3/2 RT. Okay, so 3/2 R comes out constant. dt/dt is nothing but 1. So Cv equal to 3/2 R. Cv equal to 3/2 R. For a monoatomic gas, whether it gives in the exam or not, we can happily take Cv as equal to 3/2 R. It's a known value. Okay, now we have another relation also. What is the relation between how to calculate Cp? Okay, Cv equal to 3/2 R for a monoatomic gas. We have the relation Cp minus Cv equal to R. Therefore, Cp equal to R plus Cv. Okay, Cv equal to 3/2 R. Okay, R plus 3/2 R. Okay, 1.5 plus 1, nothing but 2.5. That is nothing but 5/2 R. Okay, Cp equal to 5/2 R. Whether it is given in the exam or not, whenever we are talking about monoatomic gas, we can take Cv as equal to 3/2 R, Cp as equal to 5/2 R. Then what is the ratio of specific heat gamma? Ratio of specific heat gamma is equal to Cp by Cv. So Cp is 5/2 R, Cv is 3/2 R. Okay, 5/2 R by 3/2 R, we'll get 5/3. 5/3 is 1.666 or 1.67 we can take. So gamma value, whether it is given or not, right, whenever we are talking about monoatomic gases, ratio of specific heat Cp by Cv is equal to 1.67. This is for monoatomic gases like helium, neon, argon, etc. Now diatomic gases. Now for diatomic gases, here each molecule contains 2 atoms like this. Okay, like H2, N2, O2, homonuclear, or HCl, CO, like that, heteronuclear molecules, whatever it is. Now this entire molecule can move along x-axis, can move along y-axis, can move along z-axis. Means, right, here also there are 3 degrees of freedom of translational motion. Okay, 3 translational motion degrees of freedom. Okay, moreover, this molecule can rotate about some axis. Okay, if I can imagine one axis like this, this molecule can rotate, these 2 atoms can rotate like this. They can have some moment of inertia I equal to mr square about this axis. Okay, rotation is also 1 degree of freedom. Apart from translation, the molecule can have energy due to its rotational energy. Means this motion about this axis, rotational motion about this axis is an additional degree of freedom. Okay, similarly, I can can make these two atoms rotate about this axis also. I am putting this pen perpendicular to the board. These two atoms can rotate like this also. Or when I put the pen like this, these two atoms can rotate this way. Or when I put the axis like this, okay, these two atoms can rotate like this also. Means there are two rotational degrees of freedom. But I cannot make the axis like this because atoms are assumed to be points. There is no mass distribution about this axis. Okay, atoms are taken to be point masses. Okay, right, when I take the axis like this, one mass is here, one mass is here, mr square. There is some mass distribution at some distance from the axis. But if I take the axis like this, okay, if I take the axis like this, there is no mass distribution about the axis. Okay, entire mass is on the axis only. So this axis of rotation is not possible. Only two axes of rotation are possible. One is this and the other one is like this. Means this diatomic molecule can have two rotational degrees of freedom only. Okay, so there are 3 translational plus 2 rotational degrees of freedom. Okay, totally 5 degrees of freedom. 5 degrees of freedom we call. Okay, diatomic molecule on the whole has 5 degrees of freedom. Okay, right, now for each degree of freedom average energy is half kT. So for 5 degrees of freedom, the total average energy E equal to, right, half kT into 5, that is equal to 5 by 2 kT. Okay, this is for one molecule. For 1 mole of gas, in 1 mole of gas there will be Avogadro number of molecules. So the total kinetic energy of all the molecules in 1 mole, we call it as internal energy. Internal energy of the gas taken, U equal to, right, 5 by 2, right, kT into N, Avogadro number. K into N is nothing but our gas constant R. So we can write this as 5 by 2 RT. Okay, so internal energy of an ideal diatomic gas is U for 1 mole is equal to 5 by 2 RT. Okay, now what is molar specific constant volume as before? Okay, CV equal to du by dt. Okay, right, what is d by dt of 5 by 2 RT? Nothing but 5 by 2 R. Nothing but 5 by 2 R. So CV for a diatomic gas, molar specific constant volume for a diatomic gas is 5 by 2 R. So CP equal to CP minus CV equal to R, or CP equal to CV plus R, that is equal to 5 by 2 plus 1, nothing but 7 by 2 R. 7 by 2 R. Okay, so the ratio of specific heats CP by CV is nothing but our gamma. Okay, gamma equal to, okay, CP by CV equal to, right, 7 by 2 R by 5 by 2 R, nothing but 7 by 5 is equal to 1.4. Okay, gamma for a diatomic gas is 1.4. Okay, these things can be taken for granted whether it is they are mentioned in the exam or not. If you simply say the diatomic gas and wherever you have to use gamma, you can take it as 1.4. Okay, air. What is air in general? Some 78-79% of air is nitrogen, which is the diatomic gas N2. 21%, about 21% of air is oxygen, O2, that is also diatomic gas. Means 99% of what you call air is diatomic only. So therefore, gamma for air is also 1.4. Okay, so gamma for air, we take it as 1.4 because 99% of air is nothing but diatomic gases only. Okay, CO2 also will be there. CO2 also can become a linear triatomic molecule. It is equal to, okay, diatomic gas only. So we can happily take gamma is equal to 1.4 for air. Okay, right. Next one for triatomic gases. Third one, triatomic gases. What are triatomic gases like H2O? Okay, right, CO2, etc. SO2, N2O, like these are all what you call triatomic gases. 3 atoms are there. Whenever I am talking about 3 atoms, the question is how those 3 atoms are arranged in a molecule. If they are all in one single line, I'll call that molecule as a linear triatomic molecule. The best example for linear triatomic molecule is carbon dioxide. Okay, carbon and the 2 oxygen atoms are in a single line. okay, or in a single line. So this is called linear molecule. CO2 is called a linear triatomic molecule. Okay, whereas H2O, right, in chemistry you must have studied, okay, H2O structure is like this. Okay, right, there is some angle of some 107 degrees or 109 degrees. Okay, this is called a bent molecule. This is called a bent molecule. It is not in a, all the three atoms are not in a straight line. Okay, so this molecule is a bent molecule or non-linear molecule, we call. It is not linear molecule. So triatomic molecules can be of two types, linear and non-linear molecules. Okay, now we have to see independently what is gamma for a linear molecule, what is gamma for non-linear molecule. Okay, so first we will take the case of linear molecule like CO2. Okay, for linear triatomic molecules, that is case 1. Okay, case 1, linear triatomic molecule. Linear triatomic molecules like CO2. Okay, CO2, the situation is like this. This entire CO2 molecule can move along x-axis, can move along y-axis, or can move along z-axis. Means, right, this molecule has 3 degrees of translational motion freedom. Okay, 3 translational degrees of freedom it has. Apart from that, I can make this molecule rotate about this axis like this. Okay, or I can make this molecule rotate about this perpendicular axis to the board, axis which is perpendicular to the board also. C will be at the center, these 2 oxygens are on either side, there is some mass distribution about this axis, mr square, moment of inertia will be there. I can make the molecule rotate, means, right, here also, but there is no moment of inertia about this axis. Why? The 3 atoms are on that axis only, and atoms are taken as point masses. Okay, so there is no mass distribution about the axis, R will be equal to 0. So linear triatomic molecule has what you call, has 2 rotational degrees of freedom. So here also 3 translational plus 2 rotational, totally 5 degrees of freedom. Totally 5 degrees of freedom. So when 5 degrees of freedom means the average energy per molecule will be equal to 5/2 kT for one molecule. For 1 mole it is into n into k is nothing but r, 5/2 RT. Okay, right, du, this is nothing but our internal energy, du by dt is nothing but Cv. Okay, Cv equal to du by dt is nothing but 5/2 r. When Cv is 5/2 r, Cp will be equal to 7/2 r. Cp by Cv equal to 7/5, gamma equal to, right, 1.4 as what we got in diatomic cases. So means linear triatomic molecules are equivalent to diatomic molecules only with gamma value 1.4 or 7/5 is nothing but 1.4. Okay, right, there is no difference between a linear triatomic molecule and a diatomic molecule. Gamma is same for both. Okay, because degrees of freedom will remain same. Okay, now next one. For non-linear, second case, non-linear triatomic molecules, case 2 we take. For non-linear molecules, like H2O, best example H2O. Okay, H2O is a bent molecule. The structure of H2O molecule is like this. Structure of H2O molecule is like this. Now again, how many translational degrees of freedom? This entire molecule of 3 atoms can move along x-axis, can move along y-axis, can move along z-axis. Okay, means H2O molecule has 3 translational degrees of freedom. Okay, 3 translational degrees of freedom. Next one, I can make this molecule rotate about this axis. I can make this molecule rotate about this axis like this. Okay, oxygen molecule, oxygen atom is on the axis, but H2 molecules are at some distance. So I can make this molecule rotate like this. Or I can make this molecule rotate about its center of mass from here also. Okay, all the 3 atoms are distributed on all 3 different places about the axis. So I can make this molecule rotate about its center of mass about this axis like this, passing through center of mass. Okay, so this axis of rotation is possible, this axis of rotation is also possible, and this axis of rotation is also possible, because here molecule is not linear. Okay, for this axis also there is some mass distribution. Oxygen is on one side, two hydrogens are on the other side. Okay, so here there are 3 rotational degrees of freedom, 3 translational plus 3 rotational. So total number of degrees of freedom is equal to 6. 6 degrees of freedom they have. 6 degrees of freedom. Okay, so as usual, the energy of each molecule will be equal to average energy per molecule per degree of freedom is half kT. Every molecule has 6 degrees of freedom. So for each molecule, half kT into 6 is nothing but, okay, 3 kT. Okay, the total energy of, right, for 1 mole of entire gas is nothing but internal energy U equal to 3 kT into N into K is nothing but R, so it is simply 3 RT. Internal energy is 3 RT. When internal energy is 3 RT, what is CV equal to? Okay, CV equal to du by dt. Du by dt is nothing but, differentiate this with respect to t, you will get 3R. Okay, when CV is 3R, Cp equal to CV plus R, that is nothing but 3R plus R is nothing but 4R. Okay, so the ratio of specific is gamma equal to Cp by Cv equal to 4 by 3. Okay, nothing but 1.33, something like that. Okay, so this is for a non-linear triatomic molecule. Okay, now here we are getting 2 cases. Let us sum them up. For monoatomic gases, Cv is equal to 3 by 2R, Cp equal to R, I will write like this, Cv here, Cp here, gamma value here. Okay, for monoatomic gases. For monoatomic gases, 3 by 2 R. Cp is 5 by 2 R. Gamma is how much? 5 by 3, right? Nothing but 1.67. This is gamma value. For diatomic gases, okay, Cv equal to 5 by 2 R, Cp equal to 7 by 2 R, gamma equal to 7 by 5 or 1.4. Okay, for triatomic gases, here we got 2 cases, linear and non-linear. For linear, it is same as diatomic gas only. For non-linear triatomic gases, okay, this is how much? 6 degrees of freedom. So it is 3R, this is 4R, and this is 4 by 3 equal to 1.33. Okay, so these are the relations between, these are Cp, Cv and gamma values for monoatomic, diatomic and triatomic gases. We can take them for granted actually, whether they are given, mentioned in the question or not. Okay, right, now one more thing what you have to observe is, right, as monoatomic means only 1 atom will be there in the molecule, diatomic means only 2 atoms, triatomic means 3 atoms will be there. As the number of atoms in the molecule keeps on increasing, number of degrees of freedom also will keep on increasing. Here we have only 3 translational degrees of freedom. Here 3 plus 2, okay, 5 degrees of freedom we got here. Okay, here we got what you call 6 degrees of freedom. 6 degrees of freedom. Number of degrees of freedom is increasing. Number of atoms in the molecule is increasing. Gamma value keeps on decreasing. From 1.67 it became 1.4 and it becomes 1.33. Okay, right? So as number of degrees of freedom keeps on increasing, okay, gamma value of the gas keeps on decreasing. What is the relation between number of degrees of freedom and what you call gamma value? There is one formula, right? Gamma equal to 1 plus 2 by n. Gamma equal to 1 plus 2 by n you can take. Okay, right? Gamma equal to 1 plus 2 by n, where n is number of degrees of freedom. Where n is number of degrees of freedom. For monoatomic, 3 degrees of freedom. So 1 plus 2 by 3, nothing but 5 by 3, 1.67. For diatomic gas, 5 degrees of freedom. 1 plus 2 by 5, 1 plus 2 by 5, nothing but 7 by 5, gamma equal to 1.4. Okay, for triatomic, non-linear gas, okay, non-linear atom molecule, 6 number of degrees of freedom are 6, that is number equal to 6. The 1 plus 2 by 6, that is 1 plus 1 by 3, nothing but 4 by 3, 1.33. So as degrees of freedom, number of degrees of freedom keeps on increasing, gamma value keeps on decreasing. Okay, right? Then we'll see the most popular way of asking questions from this specific case is they'll take he will say some 2 moles of monoatomic gas is mixed with 4 moles of diatomic gas. What is the gamma value of the mixture? Okay, such problems are very popular in competitive exams. Okay, those will be discussed in our next video. Thank you.